Good morning, good afternoon, good evening, wherever you are. Thank you, and thank you for joining this talk on dam break wave in river tsunami tidal bar. I want to thank the organizer for this opportunity to share my interest and passion on this fascinating topic. I will start by acknowledging a number of students, former students and colleagues, especially Sophia, Yukai, Ray, David, Pierre, Frederic, Nazanin, and many more. The focus of this talk is about a highly transient, extremely turbulent flow motion, a wall of water in translation, as illustrated on the left slide. On the left, we see a 1.5 meter high wall of water in translation, and which will continue to translate for tens of kilometers. This is not a soliton, this is not a pseudo-periodic wave. It is a surge, it is a bar. Such a surge or bar can be generated by very different physical processes. For once, it can be caused by the sudden failure of a dam. On the right-hand side, we see the failed Malpasset Dam in southern France. On the failure of the dam in 1959 killed over 450 people. Other generation mechanisms include in-river tsunami, flash flood in rivers. On the left-hand side, it's a photograph taken 3 weeks ago in southern France, and 2 people were killed during extreme flash flooding. The bottom photograph shows storm surge bar, and we may have similar processes in engineering channel. The bottom right, black and white photograph, show water canal supplying a hydroelectric power plant in the far background. Initially, the turbines were passing 270 cubic meters per second. The turbine stopped suddenly in 2 seconds. On the resulting process, that is the stoppage of the discharge in the canal, created this rejection load surge moving toward us with a person on the car on the far right for the scale. Our communities have been adversely affected by tsunami catastrophe for centuries. During the 21st century alone, hundreds of thousands of people were killed. In particular, in 2004 and 2011, observations have shown that tsunami water propagating in river can have devastating effect. This has been the case at Minami Sanriku in the bottom right. I visited the site in 2015, sorry. On the flood, tsunami water were able to find their way along the river course and penetrate deep inland, on finding the weak spot of the coastal defense very often around the river banks. On such tsunami-affected coastal zone, there are of course a number of warning signs. Interestingly, these warning signs often depict what is probably more a rogue wave, like the rogue wave of Hokusai, than a wall of water in translation. Even tidal bar, sometimes depicted idealically, and we will come back to this, can have dramatic impact. The fleet of Alexander the Great was destroyed nearly 2,350 years ago. The tidal bar in China often overtop river banks, injuring and killing people. The bottom black and white gravure shows the sinister reputation of the tidal bar of the Seine River in western France in Normandy. That bar killed thousands and sank hundreds of ships. And again, warning sign would be regularly seen along such estuaries. Of course, we know too well that the failure of a dam is a catastrophe, especially when it's a very rapid failure, like on the far right, during the failure of the St. Francis Dam on the Puentes Dam. Photographs of dam break wave are rare. The one on the bottom middle here of this slide is one of the rare photographs that I have. In this particular instance, The emergency services are nearly 1 hour of warning, and it took place in the middle of the day during a working day. Idealized condition to warn the population, and thankfully, no one was injured. As I mentioned earlier, tidal bore are sometimes very idealistically presented in social media and by a drink company as an extreme sport, tidal bore surfing. This video, which was taken by one such extreme surfer, my friend Anthony Colas, was taken in the western part of India. But tidal bore surfing is indeed extreme, and there are regularly accidents and broken limbs. I surfed myself the Garonne River in 2013, and at the second time, I ended up with stitches, 8 stitches at the back of my head on a broken surfboard, as you can see here. Now, of course, we know too well the impact of tsunami. Here we have 2 different videos, one of a small in-river tsunami in 2016, and one in Tsunami on the top, on the 11th of March 2011. In both cases, the key feature is the leading edge. The leading edge is a wall of water, extremely turbulent, propagating rapidly and having long-lasting impact on the entire water column. It's also very destructive. While the view from above in 2016 with a sunny day of a gentle in-river tsunami appear very pleasant. Going back to Tsunami on the top left, let us remember that thousands of people in that township were killed, and the peak inundation height reached nearly 3 meters above the concrete wall that we see in the foreground. A compression wave, a surge, a bore, is a major hydrodynamic shock. It is a hydraulic jump in translation. It is not a periodic wave. It is not a soliton. I encourage everyone to read the seminal discussion by Stoker and Lighthill in their classical text, Water Waves and Waves in Fluids. One may analyze a positive surge using a system of reference in translation with the surge forms by applying the equation of conservation of mass and conservation of momentum in the integral form. And they lead a series of relationships between the flow condition, upstream and downstream of the surge, as a function of the Freud number. And in front of you, you have one such expression which is very general and valid for any cross-sectional shape. In this expression on the left-hand side, we have the ratio of the conjugate cross-section area. On the right-hand side, some of the terms like B prime and B are directly related to the shape of the water course. But while this expression is theoretically correct, it does not provide fine detail on the turbulent processes. We need field measurement like this one. This is some field work we did in 2010 in the Bay of Mont Saint-Michel, Western France, with colleagues from the University of Caen. Both graphs show for about 10 seconds the variation with time of the water depth, longitudinal and vertical velocity component. We see a transient deceleration and very intense turbulent mixing. So, what the hell? What are the key challenges? For once, we are dealing with extremely turbulent flow, very often at large Reynolds number up to 10 to the 8. This photograph in front of you, taken at the outskirts of the city of Hangzhou, corresponded to a Reynolds number about 4 10 to the 7. And potentially, the failure of a mega dam could lead to a dam break wave with Reynolds number way in excess of 10 to the 8. Secondly, we are dealing with an unsteady 3-dimensional flow. This is clear here in this photograph. We are not dealing with a 2-dimensional or even a 1-dimensional flow. It's also a very rapid process. This graph shows the variation with time of the water elevation on the free velocity components measured in the Garonne River during the passage of the tidal bore. we see a very rapid deceleration with deceleration rates of up to minus 0.3 G to minus 0.5 G within a time span of barely 1 second. The extreme turbulence generated by the surge has the capacity to uplift huge amount of sediments, leading to measured suspended sediment concentration well in excess of 20 to 50 kilograms per cubic meter, with even record observation of 150 kilograms per cubic meter in the Garonne River on the Hangzhou Bay. And all this sediment is advected by the fast-flowing flood flow, leading to very large sediment transport rates. Here, a field observation in the Garonne River in 2013, showing the sediment transport rate per unit area, kilogram per second per square meter, as a function of time for the first hour following the passage of the bore. And we see two peaks in sediment transport rate, one likely corresponding to surface erosion, and the second one associated with plastic deformation and mass erosion of the sediment bed, something which has also been observed in the Bay of Mont-Saint-Michel and well discussed and nicely discussed by Bernadette Tessier more than 25 years ago. And not only we are dealing with very high sediment concentration, but we are dealing with fine material, sediment size between 2 to 50 microns in the Garonne River and in the Bay of Fundy. And this leads to a water solution, to a sediment-laden water solution with non-Newtonian thixotropic properties. We are dealing with a sediment-laden water solution which behaves very much like cosmetic cream or tomato ketchup. Yes, tomato ketchup, rather than traditional Newtonian fluid. It means that in terms of the modeling, we need, in addition of continuity and Navier-Stokes equation, to introduce a constitutive law for this non-Newtonian solution. Constitutive law that we don't know. And then when we have a breaking bore, we have the entraînement. That is, we have now three phases: water, sediment, and air. And in this bore, suspended sediment concentration were measured of the order of 50 kilograms per cubic meter by Chinese colleagues, and the void fraction was likely well in excess of 20%. For those who are not familiar with multi-phase flow, a void fraction of 0 would mean water. A void fraction of 100% means air. And generally, a void fraction greater than 0.5 to 0.8% will make the water column opaque with a whitish appearance because of the reflection of the light on the bubble interface. But we have also a problem that air is not uniformly distributed. These are observations in a breaking roller, physical data in the foreground, CFD data in the background, showing the distribution of air in white, blue in water, within a breaking roller. And as we can see, it's a very difficult process. A breaking bore is also a very dissipative process. At the time of this photograph, based upon the observation we undertook at the time, the rate of energy dissipation was of the order of 300 megawatts. For a process lasting on that day for nearly 3.5 hours, thus dissipating 3 terajoules. 3 terajoules. So, what's next? I believe that our professional and research community need to refocus in two key directions. One, public safety. The photograph in front of you is not a fake. It's not a Photoshop. I took that photograph. I was with my friend Sophia and Pierre. We were less than 20 meters away, and we had to run for our life. Currently, there is a blatant lack of guidelines for the safety of individuals in surging water. We continue to rely upon guidelines of safety of individuals in flood waters. Guidelines like this one, which shows the water velocity on the vertical axis, the water depth on the horizontal axis, on the dashed blue line being the so-called guidelines. If you are beneath this blue dashed line, you are supposedly safe. Are you? I undertook some field measurement in a major flood of the Brisbane River in January 2011. And we worked in conditions where the measured velocity and the measured water depth are highlighted by these two pink or purple potatoes. And it was bloody unsafe. Simply, our current guidelines for safety of individual floodwaters are obsolete, inadequate, and unsafe. And by the way, North American and European guidelines almost match the Australian guidelines. I think we need to rethink a little bit this topic because we are likely failing our communities. Currently, the best that we can say is if you see a bar, if you see a surge ahead of a flash flood, ahead of a dam break wave, ahead of an river tsunami, run for safety, run for higher ground. Is it enough? A second key direction is we need a total rethink of our scientific approaches. We cannot continue to ignore the interaction between water, sediment, and bubbles, turbulent sediment bubble interaction. We need to undertake detailed three-phase flow investigations. We need also to acknowledge the strong three-dimensionality of the turbulent processes with very intense transient turbulent motion and transverse mixing. And what about the relevant time scales? Now, in a macro-tidal history, where tidal bore may take place, we know that the flood tide may last from 2.5 hours to 3.5 hours. In 2004 and 2011, we have seen in-river tsunami with a flood flow duration anywhere between a few minutes to 30 minutes. We also know that in a natural history, the turbulence integral time scale is between 0.1 to 1 second, and we saw earlier on that the passage of a surge lasts barely a second. But more recent work have shown some very complicated interfacial processes. In front of you are high shutter speed photographs taken in a breaking bar roller. And for the scale, the needle that you see is 0.8 millimeter in diameter. We found fascinating and steady air bubble entraînement interfacial processes which bring relevant timescale right down to the Rayleigh timescale for capillary breakup of about 1 microsecond, while some of the interfacial processes take place typically within 1 to 10 milliseconds. Thus, we are now dealing with a complicated turbulent flow with relevant timescale spanning over 10 orders of magnitude. 10 orders of magnitude. In conclusion, a couple of slides. Positive surge, bar, compression wave are highly transient, rapidly varied pre-surface flow, and may be found during in-river tsunami, flash floods, dam break wave, tidal bore. They are extremely complicated, three-phase flow, highly dangerous, and they involve a very broad range of relevant turbulent timescale spanning over 10 orders of magnitude. By the way, the video was a tidal bore of the Chanson River in Hong Kong. I will leave you with a key question. How can we define, characterize, measure highly transient turbulence in bore and surges at a sub-second scale for a geophysical process that may occur once a century for an in-river tsunami, to barely once or twice a day for a tidal bore during spring tide condition? Lest we forget the many victims of natural disaster caused by surge and bores, with here a memorial at Minami San Rico. Ladies and gentlemen, thank you very much.